Recording. So we are super happy to have David Cassidy here today from University College London. And well, I mean, if you Google him, you get to a Wikipedia page of David Bruce Cassidy. And it turns out that he was an American actor, singer, and songwriter, and a guitarist, and that he died in 2017. So, David Cassidy, who are you?
Well, I'm still alive, at least for now, so that's good.
Well, yeah. So me and David, we know each other from University College London, and he arrived there basically when I left, and he is one of the owners of the only positronium beams in the world, or a few positronium beams in the world, and he still considers it an atom, which is weird, but maybe he can later tell us why. So David, we are super happy to have you. Let us hear your talk.
Yeah, thank you for your classic Arnie style intro. So I will share my screen. Right, so I'm going to talk about some positronium experiments that we've done. There are people at your institute who have done this measurement already. So maybe you are aware of this, but maybe not, because it was quite a while ago, back in 1993. And so nothing has happened since then until this new measurement that I'm going to talk about today. Sorry. So I'm going to show some data that's already published, but also a lot of it is not yet published because we're still trying to figure out what's going on. But if you want some more information, you can find it in some of these papers here. So a lot of people have contributed to this effort. I won't go through them all, but here's a list of names. And the main person here, Lokesh, is the PhD student whose thesis work this was. And we collaborate with various other people too. So basically, as has previously been alluded, I do consider positronium to be an atom. And in some ways, it is the best atom because it doesn't have any of the complications that even a simplistic system like hydrogen has, where you don't know the proton radius. Again, that's an issue that some of you will be quite familiar with. Oh, sorry, my coffee machine is just cleaning itself. Sorry about that noise. Anyway, so in positronium, you basically just have this Coulomb system with two point particles, and therefore there's no internal structure to these particles at all. And so in principle, you can calculate anything you want. Obviously, you can't really calculate anything you want because you have to do these QED expansions, which get unbelievably complicated. But on a simplistic level, you can just consider it to look like a hydrogen system that's been scaled by this reduced mass factor of 2. So you get something like half of the hydrogen energy levels. That means that you've got Lyman alpha radiation at 243 nanometers instead of 121. You've got lifetimes that are basically a factor of 2 different from hydrogen. So the system is easy to understand. We have been doing experiments with positronium since 1951 when it was first invented, but nothing really with lasers until quite recently, partly because of difficulties in making beams. So the early experiments were all done in MIT by Martin Deutsch using radioactive sources put in gas cells. And so the positronium would get formed in a relatively large volume, which makes it almost impossible to do laser excitation or studies of that kind. So it was really the advent of positron beams that allowed more interesting experiments to be done. Here in this figure, which I can't see because it's covered up by some faces, but basically it's the structure of positronium. Maybe I can close it. So although it's very much like hydrogen, when you get into the fine structure, positronium is completely different. It has almost no relation to hydrogen at all. That's because you have additional annihilation channels, you've got much stronger spin-spin interactions and so on. So this is what the positronium system looks like. And these red arrows here are the transitions that we've been studying in these experiments. So, you know, the most striking difference when you're comparing it to hydrogen is if you look at the ground state hyperfine interval, in hydrogen it's 1.4 gigahertz, and in positronium it's 203 gigahertz. And that's almost entirely because of annihilation and the spin-spin interaction. So what this means is that if you do QED calculations for positronium, they're very, very different from what you would have to do for hydrogen. And this can be useful in some ways because you can look at certain methodological procedures that you would use in the hydrogenic case, and they would come out differently in positronium. So doing QED tests is sort of useful in a more broad sense than just understanding positronium on its own. Oops, sorry. Just some of the numbers here. So this paper here is the one that was done by some of your colleagues in Mainz a long time ago, 1993. And these are the measurements that were done back then. You can see that the uncertainties in the measurements are all on the sort of megahertz scale, whereas the theory, at least now the theory is in the sort of 80 kilohertz level. So, you know, this was a long-standing issue that we would like to correct, which namely, it happens to all of the positronium measurements that have been done. The theory is always much better than the experiments. So all measurements are lacking behind, sometimes only by a factor of 5 or so, but in other cases, orders of magnitude. So basically what we really need is a new series of positronium measurements that will address this discrepancy between the uncertainties in the QED calculations and what's been measured. So again, here are the transitions that we're talking about. So that's what I just said. So the last measurement was a long time ago. Why is this? Well, a few reasons. One of them is that the way the experiment was done before, it was kind of difficult to improve on that. So until you have a new methodology, there wouldn't have been very much point repeating that experiment because it was already kind of as good as it was going to get. One of the reasons for that is the way that the positronium was actually produced. So in order to do this experiment, we make some 2s atoms and then we fire microwaves at them and drive them into these 2p states, which then decay radiatively, and we look at the gamma rays that come from the final decay of the ground state. The production of the 2s atoms is where the problems came from before. So in the previous experiments, not just these ones, but some ones before that as well, what they did was to shoot a positron beam into some metal targets. I think molybdenum, tungsten, various others have been used. And a very, very small fraction of atoms will naturally be produced in this metastable 2s level if you do that. But it's quite small. It's on the order of 0.1% or something. So that means you don't have a lot of atoms to look at. In addition to that, this process of formation means that the energy of the atoms is necessarily quite high because the formation, you know, the binding energy of 6.8 in the ground state is reduced dramatically, and that energy has to go somewhere, and it goes largely into the kinetic energy of the positronium atoms. So what you end up with are atoms that have energies of several electron volts. And for positronium, this means they're very, very fast. So they're going to fly through your machine. You have to turn the power up quite high. You're going to get a lot of broadening effects and so on. So that's the reason why it wasn't really very feasible to improve on these previous measurements. Here's the data from the old experiments. So it's good. I mean, the measurement was very nice. They got a decent result. There was no discrepancy with theory, but the main reason for that was that the errors were relatively large. So what we've seen is that we don't agree with the theory. We have smaller uncertainties, and we also have some issues with the line shape. And so if you look at this, you could imagine that there was some asymmetries in this data that were not easy to spot because of the large error bars on all the points. And so what we have seen is that there are very clear issues with the line shape, and not knowing the line shape is a big problem for us, which I'll explain more about that later. So basically, the main differences from the previous way of doing it and the way we're doing it now is that we produce the n equals 2 atoms in the metastable state using a laser. So we optically excite them. This gives us two main advantages. One of them is that we basically get more atoms, although not a huge amount more, unfortunately. The second issue is that we're exciting ground state atoms that are produced in a different way. So the atoms start off quite slow, and then they get excited, which doesn't really change their speed. So we end up with atoms that are more like thermal instead of electron volt energies, which means tens of milli EV instead of a few EV. So this gives us an opportunity then to get much narrower lines, to use lower microwave power to avoid some systematics and things like that. Of course, there are other problems with doing it this way, but it's a different kind of experiment. It has some different systematics, and in principle can be done with much better uncertainties. And that's why we thought it was worthwhile to revisit this kind of measurement procedure. So this is a picture of the lab. I'm sure you've seen pictures of labs that look just like this before. There's not much else going on in this room. There's nothing outside of the picture, so it's quite small. We use a radioactive source to produce positrons. The old Mainz experiments were done with a LINAC, which would be really nice because then you get a pulse beam. We have to get our pulse beam in a different way. So the radioactive source is basically surrounded by a copper cone, and we freeze neon gas onto this cone at 6 Kelvin. This gives a place for the positrons to thermalize and then be re-emitted with a few electron volts of energy. We form that into a beam which travels along here. And then this black cylinder, you can't really see what's going on, but inside is essentially a Penning trap or a Penning-Malmberg trap. We call it a Serco trap, which is the same thing, it's just filled with gas. And so when the positrons go into the potential well of the Penning trap, they lose energy by gas collisions and become trapped, and then you can kick them out once per second. So you turn your DC beam into a pulse beam. That pulse beam is then implanted into materials that form positronium atoms with these near thermal energies. We use SiO2 films, but there are lots of other things that you could use instead. And then because we have a nice pulse beam, we can bunch it in time and form a nanosecond wide pulse. That means our positronium atoms are formed with a similar time profile, and then it's very easy to match them up with a pulse dye laser that has a few nanoseconds width. So that's how we do the excitation, which I'll explain more detail later. So here's just some more schematic of the thing. Whole thing's about 20 feet long and works pretty well most of the time. So this Serco traps is really another thing that has changed since the previous measurements were done. If we didn't have the Serco trap, it would be almost impossible for us to make a pulse beam that had a reasonable number of positrons in, because we would just be essentially bunching a CW beam that had maybe 10 to the 6, 10 to the 7 positrons per second. And so in a few nanosecond pulses, you get 5 or 10 positrons, which is not really enough. Using the Serco trap, you can basically store up some of the beam and then form these intense pulses. So just for fun, here's a picture of the first Serco trap. That's Cliff Serco there. If you don't know him, and that's a guy called Al Passner, who also worked in Bell Labs, where this was developed quite a while ago now, it seems. So although 1989 is when this was first done, they weren't really in common use until probably 10 years later or so. And they work very like this. That's what I just explained, basically. They lose energy, they become trapped, then you kick them out, they go into this porous material. The reason why we like the porous material is because when they're first emitted from the bulk material into the voids, they have an energy difference that's given by the difference of their binding energies, which is quite high. It's about 1 electron volt. But by colliding with these internal surfaces, they lose energy quite quickly. And by the time they get into vacuum, they're very close to thermal energies. So as I said, sort of tens of milli eV. Then we just inject that pulse into some target chamber, which we surround with gamma ray detectors. So all of our measurements are done looking at the gamma rays from the annihilation of these atoms. One of the disadvantages of our methodology is that the Serco trap necessarily has a magnetic field. And it is possible to extract the beam from the magnetic field without too much trouble, but we haven't done that yet. So what that means is all of our measurements have been done in a magnetic field. And as I'll explain, we have to account for that. So we have a little waveguide. So there's basically a positronium formation target on the other side of it. So the positron beams go through here, and then the positronium comes back in the opposite direction and flies through this waveguide. And this is where we apply the microwave radiation. So that's just a picture of it there. So the positrons come in, they fly through this thing. We don't lose very much because there are grids on the walls that have relatively high transmission on the order of 90% or more. They fly into this SiO2 and form the positronium. And the positronium atoms are made in the ground state. So this is before any lasers come out. Although the previous experiments that I mentioned earlier have a small component of excited state atoms, if you do it using these porous materials, you don't get any excited state atoms for free, because by the time they collide with the walls, they'll be de-excited to the ground state in any case. Plus, that material doesn't really support this process because it's formed in the bulk rather than at the surface. So all of our atoms come out in the ground state. If they're in the singlet state, they won't even escape into vacuum because the lifetime is so short. And so we have these positronium atoms that have lifetimes of 142 nanoseconds just flying through. So if we don't do anything else, we won't see much of a signal. If we turn on the microwaves, for example, they won't do anything to the ground state atoms. So then we have to excite them with a laser. So we have one UV laser that excites them to this n=2 level. And then if we want to, we can photoionize them or make Rydberg states using a second IR laser tuned to some other wavelength. Now, what we want to do is make metastable 2s atoms, and that's obviously not possible using a single pulse excitation, except for the fact that we do it in an electric field. So, sorry, I'll explain that in more detail later, but going to n=2 without the electric field would not be very helpful for our experiments. So the way that we observe what's going on is to look at the gamma radiation from positronium annihilation. So here's an example of that. We make a spectrum, which is really just reading out the output of the gamma ray detector into an oscilloscope in real time, if you like, and then looking at how that lifetime spectrum changes when you do something. So in this particular example, we have a laser that's tuned to excite the n=2 level and then to photoionize. So there are two lasers. And if you do that, the annihilation signal compared to when you don't have any lasers is going to show more events at early times because you've basically ionized this positronium and then the positrons get sucked back into the target and make a gamma ray pulse. So if you look at the difference between the lifetime spectrum with and without the laser, you see something like this, basically an increase in counts. So this is basically the counts relative to the 142 nanosecond decay that happens from the ground state annihilations only. So you see an increase in counts at early times and then a decrease in counts at later times. Basically, these are the ones that would have decayed over here if you didn't do anything. So the excitation is now visible in this different spectrum. And that's the main way that we look at everything that's happening. You see an excitation at some time window, and it depends very much on what the process actually is. And we can be more quantitative about what's happening by integrating the spectrums over some time windows. So A, B, C, and D would be sort of at the beginning, at the end, and then somewhere in the middle. And the B window would be set to whichever place you happen to be interested in. So in this case, you would set it somewhere around here to distinguish between this part of the spectrum and this part. So when you see this S number, you can just take that to mean that's the signal parameter. That's basically the indication of how much the laser or the microwave radiation is doing stuff to the positronium atoms.
Sorry, I just looked at something else and I didn't understand why you have more decay now when the laser is on. Like at the beginning.
Sorry, you mean not this?
I mean this.
Okay, well, in this is an example of ionization. So the positronium atoms come out in the ground state, you excite them and you ionize them, and then the liberated positrons will decay because they go back to the target.
Okay. Sorry.
So if they didn't decay, then you wouldn't see this. You would basically see kind of the signal diminishing.
No, I thought it's the laser that puts it into the n=2 state, but it's like ionizing. So okay.
Yeah. This is just an example. I will show you some data where that happens as well in a minute. So basically, that's what this is trying to explain here. Now, if you do something different, so if you don't ionize them early, but instead make them into something that lives for a long time. So in this particular example, we made some Rydberg atoms that have n=8. So they have a lifetime of about 1 microsecond before they decay back to the ground state. And then after that decay, they will annihilate with 142 nanoseconds. If you do that, then you will indeed see this thing happening later. So you basically see the opposite of the ionization signal, where the early signal goes down because things that were decaying no longer are, and the later signal goes up because the lifetime has just pushed them out into this longer time region. So that's basically the basis of how we look at things. In this case, you can imagine the n=8 signal is going to look a lot like the n=2 signal, because the metastable n=2 atoms have lifetimes that are almost the same as n=8, which is the reason why we chose n=8. It's just a much stronger signal. So in this case, you would see an S number that would have some arbitrary value, and it would be different for these two things if you use the same time windows, but you adjust the time windows to optimize the signal to noise for this particular type of signal. So in the case of our microwave spectroscopy, we basically make something that lives for a long time and then try to kill the signal by converting them back to the short-lived states. I'll show you that later. So to make the 2s atoms, we can't just excite them with this UV laser. So we have to basically do this in an electric field. And there are other ways we could do this, but we just don't have the right lasers for it. So basically, probably the best way would be to just use a 2-photon 1s to 2s direct excitation, because the 486 nanometer light would be capable of ionizing the n=2 states. There's a limit to how efficient that can be. If you crank up the power, you start ionizing everything that you excite. And it turns out that you can get something like 15% of your atoms in the n=2 level this way, metastable 2s. But you've got to have a nice narrowband laser at 486, which we don't have. All of our lasers are quite broadband because most of the experiments we do are these single photon transitions, which are enormously Doppler broadened because the atoms are moving at 100 kilometers per second, which is one of our big problems. Another way that's been shown by some anti-hydrogen people is to excite directly to the n=3 level, and then you can get about 10% that naturally decay to this metastable 2s, or you can actually stimulate emission down to this level with slightly more efficiency. Again, you need a 205 nanometer laser to do this, and it's basically no more efficient than what we already do, so that wouldn't be very useful for us. So instead, what we do is we do the excitation in an electric field. That's basically just so that we can make these states that already have some 2s component mixed into them. So it's kind of the opposite of quenching. If you have a 2s level and you want to detect it, you can turn on an electric field, mix it with the 2p's, and then watch it decay. Here we do the opposite. We excite them already in this mixed state with a bit of 2s component in. Then we quickly turn off the electric field, and then we just allow them to evolve back into here. And this gives us some fraction. It's a little bit difficult to know exactly how efficient it is, but it's on the order of 5%. So the excitation is done in a field like this. And then they, with some probability, go back to here. So this works reasonably well. We get a decent signal. The only problem is we can't quite turn the fields off as fast as we would like. You have these switches that have 10 or 20 nanoseconds or something, and the lifetimes go down quite fast. So, if we were in zero field, you would have a lifetime of about a microsecond. By the time you get out to half a kilovolt per centimeter, it's gone down to a pretty low level. So we have to turn it off quickly. And if we could do it a little bit faster, it would be more efficient. But other than that, it's a reasonable approach. So here's just an example of how that works in terms of the timing of it. You have basically what we do is we turn the field off after the positrons have been implanted, but before the laser excitation happens. This is just a technical thing. You have to have a certain implantation energy into the target for the positronium to be made deep so that it has enough time to collide and cool down on the way out into vacuum. Otherwise, you'd get atoms that were too hot. So that sets the impact energy that you want. But you don't necessarily need to do the excitation in such a high field. So if we turn the field off and then turn the laser on after a small delay, then we can basically minimize the time that the excited state atoms spend in a relatively large electric field and increase the probability of making these 2s atoms. So the upshot of all this is that you basically have a laser firing some switches turning off voltages, and you end up with what I would very loosely call a beam traveling through this waveguide in a metastable 2s state. There will be some ground state atoms that make it through here, but not very many. That just constitutes a background in the lifetime spectrum, so we don't have any effect from that. So then the experiment's very simple. You do this and you get some kind of time profile for the decay of these guys. Then you turn on the microwaves and you convert some of these 2s atoms to 2p. They decay in 3 nanoseconds to the ground state, and the ground state decays in 140 because of the difference in this 2s lifetime, excuse me, versus this one. Sorry, the 2p lifetime.
Was it just my internet or was it your internet?
So, I don't know, I think it was mine.
Because I saw Randolph was still moving, so...
Yeah, I also didn't hear anything in the last 10 seconds.
Oh, okay, sorry. I was just saying that, basically the simple version of everything I've just said is that you make these ground state atoms here, the excitation and field process converts to the 2s state, and then those fly through this waveguide. It's located close enough so that most of them go through, but a few of them will be lost if they have wider trajectories. So it's kind of like a beam, but not really. It's diverging a bit too much. But nevertheless, oops, sorry. That's not supposed to happen. So if you do this, you get a certain time profile in the annihilation radiation. And if you then turn on the microwaves, you basically watch them decay into the 2p level, and that changes the time profile of the microwave radiation. And that's how we detect what's happened with the microwaves. So it's fairly straightforward, even though it involves a long series of connected steps that's kind of awkward. The basic principle is fairly straightforward. So, oops, here's just the same thing again. We have the microwaves traveling this way. This forces the polarization and it has to be perpendicular to the magnetic field. So that means that we're only going to be driving delta M equals 0 transitions for the most part. There could be some funny things happening in these grids that we don't know about. But as far as we can tell, we only drive one kind of transition, which simplifies things a little bit. And we have to use a different waveguide for these transitions because, well, we could probably get away with using one waveguide for 2 of them, but then you'll be a little bit close to the cutoff frequency, and this has an effect that we wanted to avoid. So we made a separate waveguide, but put this frequency right in the middle of it, as close as we could anyways, to each transition. So the disadvantage of that is that we have to open the system and extract it when we switch from one to the other. So we weren't able to measure different transitions interspersed with each other. We had a campaign of one frequency and then of another and then of another. I'm not sure that was a big problem. So here's an example of the time spectrum that you get here for the 2S production only. So this is basically just turning on the laser to excite into the n equals 2 level, turning off the electric field to produce some of these n equals 2 atoms, but then not doing anything else, so no microwaves. And you can see this looks very similar to the n equals 8 Rydberg signal that I showed earlier, which it should do because it's the same lifetime almost. So then if we turn on the microwaves, we basically force these guys to annihilate earlier. So this looks a little bit more similar to the ionization signal that I showed you before, except it's much delayed relative to that. The reason for that is just that you have to wait for them to fly into the waveguide. And we use quite low power. So the time that they spend in the waveguide is also on the order of 100 nanoseconds. So other than that, this is very similar to the ionization signal because it's kind of a similar process. You're just forcing the annihilation. What we have to do as a function of the microwave radiation. Here's just another example of that. Right, so we can integrate over these time windows that are set here, and that gives us this number S gamma, which is basically just a measure of how much stuff there is in this part of the spectrum compared to this part. So you can see if the rest of the signal was in this part, it would be very different S gamma to this, where S gamma is just the way it was defined earlier. So when you scan across the microwave frequency, you get some resonance peak, and that's essentially all the measurement really is. We fit Lorentzian functions to them. We don't think there's any need for Voigt functions, and in any case, the data quality is not really that good. So Lorentzian seem to do the job quite well. So this is all well and good until you do it for different measurements. And then we have some problems. The problems are that we don't have nice time shapes. And so there's a few possible explanations for this, but none of them seem to give shifts that are big enough to account for what we actually observe. So in this particular case, I'm showing example line shape. So in reality, we measure this many, many times. So we have literally hundreds of these, and then we average out the fit parameters that we get from them. And for this transition, which is the strongest one, you can basically see it with your eyes that it's quite asymmetric. For this transition here, you can't see it quite so clearly, but it is asymmetric as well, but on the other side. So the line shape is distorted in the opposite way. However, for this one, for the new 0 transition, we don't see any asymmetry. And so obviously we don't just look at them and say, oh, that one's asymmetric and that one isn't. We have to have some kind of parameter to determine if there is in fact any asymmetry. And to do that, we use a Fano function, but we could use any function that allows an asymmetry parameter. So this is not to say that the Fano function is the proper description of this. It isn't at all. Or if it is, we don't understand what the Q value is. But actually what we really just want is a way to characterize line shapes as being asymmetric or not asymmetric. So we fit this Fano parameter because it has a built-in asymmetry parameter that we can take advantage of. I don't expect to see anything like this, but what we do see are line shapes that basically look skewed one way or skewed the other way. And if you have a large Q value, then you don't see anything, and this thing basically approaches a normal Lorentzian function. So once again, we're only using this to determine if these line shapes are asymmetric or not. We're not saying that the Fano function is the correct line shape model for this, because I think it definitely isn't. So what we end up with then are these Q parameters. And so you can see here, this one has Q equals plus 10. So if I go back to here, that's kind of like this one. this here has Q equals -12, so that's the same, but in the opposite direction. And here it's like thousands and thousands. And so we end up with very large Q values for all of these transitions. So this one doesn't seem to have any asymmetry. So on that basis, we think we can say that we can extract an actual resonance frequency from these data. But from these ones, we really can't, because we don't have the proper line shape model. It's not correct to just fit Lorentzi into it, because the asymmetry forces the peak to move around. And this is a particularly annoying problem for this, because it's 50 megahertz wide is the natural width. What we actually measure is a little bit more than that. And we think that's because there's a little bit of transit time broadening as they fly through the waveguide. But it's not a lot more, it's 50 to 60 megahertz or something. However, if you have a 60 megahertz wide line and you're trying to extract the centroid position to sub-megahertz, then any distortion in the line shape is a big problem. So the position that we have now is that we can't actually say what these frequencies really are, because we don't know what the line shape model should look like. In this case, we think we do, but it doesn't work, because we end up with something that doesn't agree with theory, which is a problem when the theory is QED, which most people probably think is true. So here again, I'm just going to show you the previous measurements done at Mainz in '93, and you can see that it's possible that there's some asymmetry here, but I wouldn't like to say one way or the other. I don't know if this was looked into in any more detail or not. But we have now a much better signal to noise ratio, and I think it's pretty clear that these line shapes are asymmetric. And when we do this many, many times, we end up with very consistent values for these Q numbers here.
Was the experiment in Mainz also limited by the lifetime of the atom?
Well, the natural width is the same, of course, but they have very fast atoms. So I think they have to use much higher powers, which causes some power broadening as well. There may be some transit time effects too, because the atoms are flying through similar size waveguides, but much, much faster.
That's correct. That's correct. We need higher power.
Right. Okay.
Yeah.
David, what about residual Doppler shift? Do you see that?
I don't think so, but it's possible. So I'll get to that in a minute. That's probably our biggest systematic, because we're not entirely sure. But one advantage of this technique is that when you use the laser to do the excitation, the bandwidth of the laser selects a small slice of the velocities in that direction. And that's the direction that they spread out in the waveguide. So the Doppler broadening is reduced because of this. Now, if the laser's not lined up with the waveguide properly, then you're going to have a problem where you get some shift in one direction or the other. And then you could have an effect of that. But for any reasonable numbers, this would amount to hundreds of kilohertz or something like that. So I don't think that's a problem. Also, I don't think that can give this kind of asymmetry in the line shapes. But I'll talk more about that in a bit. So anyway, because we don't have very high power, we can get close to the natural width. You can see here, these ones are like double or something. So, I think that the data is clearly telling us something. We just don't actually know what it is. So the other problem that we have is that we're doing this in a magnetic field. And so that's not really how you want to do it. And obviously one of the things that we plan to do is to get rid of the magnetic field entirely. But because we weren't able to do that in this particular measurement, what we did was just measure it in a bunch of different fields. So this is what happens to those transitions from Zeeman shifts. So in this new zero case, this is the one that doesn't appear to be asymmetric. There's only one transition, because we think anyway that we only have these delta m equals 0 cases. So that means here we can only go from this metastable 2s m equals 0 down to this 2p equals 0. And there's also only one p state anyway for this. So this is possibly related to why it's not asymmetric. In this case, you've got other transitions that you can do. And here there are actually two possible transitions. So if you work out what these shifts should look like in a function of the magnetic field, in these two cases, they have only one shift. Here, there's two different transitions that are slightly shifted, but they're not very different from each other. So you'd expect to see something that looks a little bit like these lines here. These have been weighted by the transition strength. And so the idea is we just do the measurements as a function of B and then fit. So these are all going to be quadratic, of course. And so even if we don't accurately know what the magnetic field is, we think we can just still fit a quadratic function to this. However, this is a huge waste of time, right? Every one of these measurements has to be done over a course of many days. It would be much better if we could just measure one zero field case and have the statistics of all of these points bundled into one measurement, but sadly not. So that's the reason why this took us a year to do, because we had to keep doing it over and over again. So what I've done here is to fit Lorentzian functions and Fano functions to the data, even though neither of them are probably correct, just to show that they give sort of slightly different numbers, which is all to do with how well you can extract a peak from it. None of these numbers are real numbers, by the way. I just think you can see clearly here that the Zeeman shift does more or less what you think it should, but they don't approach what you think the zero field values ought to be. And in this case, where there's no asymmetry, so we do think this is actually the correct case. You can see there's not very much difference between the Lorentz and the Fano. That's exactly what should happen when you have large Q values, but you can see that none of these points want to be anywhere near this line, except this guy. And so we're not going to get the right value when we extrapolate this back to zero.
Did you use the same Q value for the top two plots? Or did you just let it as a free parameter and then see what fits?
No, each one of these points is a fit where the Q value is a free parameter and they all come out to be more or less consistent with each other. So the degree of asymmetry doesn't depend on the magnetic field. I can show you those parameters versus B in a bit. So yeah, we're not forcing anything here. We're just fitting these two functions on their own and they kind of give consistent results, but we don't believe any of those numbers to be the true numbers. That's the problem. So in any case, what we do then is extract these guys back to zero just by fitting a quadratic function, because you know the physics tells us it should definitely be quadratic in B, and that's what we get. So what you see here then is that the extrapolation of using these wrong functions gives you either a positive or a negative shift from what is most likely the correct answer, the theoretical answer. In the Lorentz case, it's clearly just a function that doesn't fit the data properly because it's asymmetric. And in the Fano case, well, it returns a value, but it's not the true value because there's no reason why it should be, because it's not genuinely a Fano function. I'll show you what happens when you just take the peak of that later. That actually gives you something in between. But in this case, you get more or less the same answer, regardless of which one you use. That's why we think this is probably true. But as you can see here, there's a huge difference. I mean, it's nearly 3 megahertz away from the theory. And if you're 3 megahertz away from a QED number, then you've got a problem, I would say. So in this case, we're not claiming to know the answers basically for these numbers. Now you could make some argument and say that maybe it's somewhere in between the two. Obviously that's what it looks like from the data, but there's not really any physical reason for this. So I think the conclusion that has to be drawn from these data is that we desperately need a proper line shape model, and we need to understand the source of the asymmetries in those peaks, which at the moment we don't. In this case, okay, you can say that you don't have an asymmetry, but you can still have a shift caused by some kind of interference phenomenon or something that would give you an asymmetry in some cases and not necessarily in this case. So it's entirely possible that whatever is causing these two things to be asymmetric is causing this to be shifted without making the line asymmetric. So I don't know how to do that, but I don't say that that can't happen. So I think, you know, if one of them's wrong because of some mystery effect, and there's no reason to say that it won't happen in all of them. The real difference here, though, is that you only have one possible transition in this case. And here you've got a couple of different ways to get to the same place. And so that kind of strongly suggests maybe there's an interference issue going on. And we did look into that. Just to answer your previous question on it, this is what you get for these parameters as you look at them as a function of magnetic field. So there's a bit of scatter, of course, but they basically are more or less consistent and don't have strong field dependencies. None of them have very consistent field dependence. I guess this one could be said to do that. So we don't think that the magnetic field is the underlying reason for this problem. We think that there's something else going on. But like I said, we don't actually know what it is. So systematic effects in the experiments, well, there's a few problems. As I sort of mentioned earlier, if this laser was misaligned, then that would basically peck out some atoms that were traveling up or down, depending on the misalignment with respect to the microwave field direction. And if you work out the numbers, it's not huge. So we think that we can align this to within a couple of degrees, but we probably need to do better than that if we ever solve these asymmetry problems, because that gives you hundreds of kilohertz possible shifts. So obviously the proper thing to do, which we haven't done, but which was done in the previous experiments, is to simply reverse the direction of the microwaves and see if there's a positive or negative shift. So that's something we'll definitely do in the next round. You don't necessarily then have to know what this is. You can just figure it out from the positive and the negative shifts. In the present case, this 2 degrees thing is a guess, but it's not likely to be 5 degrees, and it's certainly not going to be 20 degrees. So there's no way to explain this enormous shift of 3 megahertz based on an alignment problem like this. We can also change the direction of the laser pulses and rotate things around and so on. Other systematics that would be a problem for people who were doing like genuinely precision measurements are not really significant on our level because we're quite far away. So, we don't have AC Stark shifts and things like that that are causing big problems because they're all like on the 10, 20 kilohertz level, and we're very far away from that so far.
What about microwave field gradients?
What about them?
Well, if it, if the spatial dependence and if there's some spatial dependence that could cause effectively shifts.
I see. Yeah, I think that this is not a cavity, right? This is just a waveguide where the microwaves are flowing through. So there's going to be some structure in there, but the positronium atom sampling all of it. So I don't think that I can't think of a way that you would pick out like a funny bit of the gradient.
Well, that with a combination of some reflection, maybe.
That's true. Yeah, there could be some funny stuff happening. So we are in the process of doing simulations to check, because what we should have also done, and which I will again acknowledge was done properly by the previous guys, is instead of just having this waveguide thing stop, it should go out and be terminated properly in a matching load, right? And we don't do that. So there may be some funny reflections that happen when you get to the end where there's obviously a ginormous impedance mismatch. One of the reasons why I don't think that's responsible for the data is that we don't see the same problems in all of the line shapes. In fact, they're all different in different ways. So that doesn't rule it out, of course, but my feeling is that that's not what's going on. As a secondary test of that, we have recently done an experiment where we don't have a waveguide at all, but we used the horn antenna. This was for the mu equals 0 transition, and we again see this quite large shift, but the data is not complete yet, so I can't say for sure that that's proved. So I can't rule that out exactly, but I don't think that's what's going on. When we finish doing the simulations, we'll be able to have a bit better idea of what's really happening at these edges, though. So that is a fair point that it needs looking at.
One question about the creation process of your positronium atoms. Of course, you concentrate on the ground state, which you excite them to rest, but at the same time, you may produce immediately N=2 positronium atoms, as we did in our earlier experiment. It's a small fraction only, but you take only, we said something like 5% of your ground state atoms to be excited into the 2s state. Mm-hmm. So the fraction of fast positronium atoms in N=2 immediately created at the surface is not that small, perhaps, at least maybe 10% or so. Would this contribute to something?
No, I don't think so, because in the targets that we use are very different from like metal surfaces. So basically the positronium is formed directly in the bulk of the SiO2, right? And in that case, the N=2 production is 0. I mean, they just they can't survive in that environment. They have to be in vacuum straight away.
Okay.
So, but let's say you did have some of them making, if they were created very close to the surface or on the internal surface of the SiO2, then they would have many collisions before they leave. So the chances are they would be de-excited before they got out. Mm-hmm. So I think even if there was some way to produce them inside, you wouldn't actually see them outside. We did test for this by firing the ionizing laser on its own, with long delays and different timings and things like that. And we never see any signal from doing this. So I'm pretty confident that there are no other N=2 atoms being produced.
I think I would agree to Dima Woodgate that probably the both structure inside the waveguide may be causing a problem. So why not simply change the size of the waveguide, just to change the reflections, the possible reflections?
You mean make a proper waveguide?
Yeah, or something different, or closing it properly, as you said, or changing length.
So we do have 3 different waveguides for one for each transition. So in principle, those would not all be the same, but of course they're matched to the frequencies of the transition, so they might track each other in some way. And using the horn antenna is not ideal either, because you get a kind of a horrible looking field structure coming out of that in the near field region where we had to do it to get the power. But we still see this same shift. So my feeling is that even if the waveguide is contributing something, it's not making an asymmetry in at least one of the transitions. So it can't be doing anything too crazy, I would say. You know, we do plan to test that in another way by having Rydberg helium atoms fly through the exact same waveguide. So we'll pick out some Rydberg states that have transitions that are very close to the frequencies that we're using, and do spectroscopy on those atoms and see if we can see anything that's we don't see in zero field. Because with the Rydbergs, you can easily do spectroscopy using microwaves without any waveguides at all, quite accurately. So I think if we do this inside and outside of a waveguide, we'll see immediately if there's a strong shift caused by the mode. So that's one test that we plan to do. But my feeling is because there's no asymmetry in one transition, there's wrong asymmetries in both of the others. I would suspect that that's not the ultimate cause of what's going on. But I definitely agree that it needs to be looked into. Okay. So anyway, when you see asymmetric line shapes like this, you probably be reminded of the work of various people, including Eric Hessels, who's done a lot of discussions about this kind of asymmetries. So you can have interference effects that aren't necessarily obvious. Here's just a sort of schematic layout of some possible things that could be happening. Now, we haven't gone through the full calculation of this, so I don't want to say too much about it, but basically there's a way to estimate the strength of these kinds of effects in a simple case where you just have, you know, a nearby transition that's separated by some number of widths, and then you can estimate what the effect would be. So the estimation is basically saying, if I have a line shape that's distorted by an interference effect of this kind, and I fit a Lorentzian to it, it will be wrong by something like this much. Okay, so this is not what we worked out. This is worked out by Hessels, and I think also by well, Randolph can say more about this, because this is features in the 2s to 4p hydrogen measurements that were done with much better accuracy, obviously, and so they had to really take this into account. Otherwise, they got an enormous shift in their data. So I just bring this up because when we look into this, so we did do a simple calculation, but we need to do a calculation that includes more states. And we don't see anything like a big enough effect. And if you just go by this rule of thumb, you also only get a few hundred kilohertz. So it's nowhere near big enough to give us our 3 megahertz shift. So I think interference effects probably exist, and we might see them one day if we do a much nicer experiment. But I think at the moment, those are too small to explain what we're observing. So now here
can I ask a question? So you have your Zeeman shifted lines, and the ones which show shifts are the one where you have the delta M plus or minus 1. They can interfere, no? If you have an incomplete initial state preparation and you make an imbalance of the different M states by your laser or by some electric stray field, which gets you some M plus 1 and M minus 1, and then they interfere, and then there is virtually zero delta. So detuning, and there you can have arbitrarily large shifts. Maybe, I mean, it's really curious that the guys which have delta M plus minus 1, they show shifts, and they show shifts in the opposite direction. This really smells like these interference effects that Eric brought up and we saw.
It does, but it's not big enough. I mean, there's no way to make it that big, as far as I can tell.
But you can have interference between the different delta M's which have the same energy.
Yeah, but it's still on this like rule of thumb level of hundreds of kilohertz, right? It doesn't ever get to the megahertz scale unless there's some unknown prefactor that you have to do a full calculation to see. Then we're just sort of way off the mark by using this estimation. I mean, we think that the transitions that we can drive are only delta M equals 0 because of the polarization of the field in the waveguide. So the other transitions are there.
Yeah, but you have M equals -1 to -1 and +1 to +1, right?
Right.
and they can interfere. And if you have an imbalance of these two guys initially, then you may have interference. It depends on, I mean, it's really difficult. You have to look into the details of what you are measuring actually, because you're looking into annihilation.
Right.
That is necessarily the same final state. And the question is, do you have, probably you also have them in the same initial state, but then you have to make the Bloch equations for the full excitation and de-excitation scheme.
Yeah, well, that's what we haven't done. So
Yeah.
that's why I can't say that this is not true, but the indications so far don't support that. I mean, if you're saying that these m equals +1 and -1 channels can interfere, then you would expect both of those line shapes to have the same distortion, right? But they're opposites, and that doesn't seem to work.
No, but that is because that depends on the final state that you're reaching in the ground state after the decay.
But those are all the same. I think what we actually measure can be taken as a sort of almost like a survival rate for the 2s, if you like. I mean, I don't know how to explain that in full detail, because we measure the time profile. So we're just sort of measuring the ratio maybe of atoms that have been driven to 2p versus those that stay in the 2s or something like that. So it could be that there's some subtleties involved in that. But yeah, I would expect, if that was what was happening, that both line shapes would have the same kind of asymmetry rather than this opposite type of asymmetry. But, you know, maybe this is not correct. But in any case, that doesn't explain the symmetric line. I think that's problematic because there aren't any m equals +or -1 levels for that. So this simply can't happen.
Yeah, but who cares if QED is 4.5 standard deviations off, right? This happens all the time.
Yeah, maybe. Anyway, I would like to have a model that explains all three of these things at the same time without any additional input. So that's what we're looking at. Anyway, so what I'm showing you here in this plot is all the data that's been done in the past. So you can see for this one, the Mainz measurement is over here. Our measurements, we don't know what they are, but these are the Fano and the Lorentzian points, neither of which are agreeing with the theory. But if you take the Fano function, so it includes the asymmetry, and just differentiate it to get the peak position, then you get this fortuitous agreement with theory. So I don't know what that means, probably nothing, but certainly doesn't allow us to claim anything. In this case, it's a similar story. The data's over here. The previous measurement, sorry, that's the Mainz one, that's Michigan. This is actually a nice coincidence, because when they did this measurement, the theory line was not here, it was somewhere else. So the theory has moved into agreement with the previous measurement, which is very accommodating of them. And we have the same problem where we've got these 2 points that are on either side of the theory. And then if we do the same thing here, we get this thing that's sort of in between the two. It doesn't quite agree, but it's a hell of a lot closer. And then in this case, where we don't have any asymmetry, so we have some dream of understanding what's going on, we don't agree with it by this much. So this is where the 4.5 standard deviations comes from. The other experiments don't disagree with us, but they don't disagree with the theory either. So that doesn't help very much. So what do we do next? We've got to figure out what is causing these asymmetries, obviously. And doing this full block calculation is something that is ongoing, but it's going to take a bit of time. Understanding whether or not this shift is actually the same effects, just manifesting in a different way, is basically going to come out of this too, hopefully. So we need to add a different antenna so we can get rid of this possibility of having a misalignment with the laser. We need a complete line shape model. That's basically kind of the same thing as this, but maybe there's some other things that need to be looked into, like exactly what are we measuring? Can we change the measurement so that we directly detect atoms instead of looking at this lifetime spectrum, which is a little bit ambiguous as to what the measured parameters really are, in the sense of, are we seeing how much is left versus what's being destroyed? Extract the positron beam out of the magnetic field, we can definitely do that. It's just a question of getting it done. So that's on the agenda. Using this Rydberg helium to map out the fields. We can also measure stray electric fields in the waveguide, but we can measure as well what the waveguide is doing in terms of the microwaves, with reference to something that we think we can measure another way with relatively good efficiency. So this will be a good test. But this also should include using different waveguides, as you mentioned earlier. I think that's a very good idea. We should definitely terminate them. We should understand exactly what's going on in the waveguides. I think it's a very fair point that what we've done is pretty crude and we don't necessarily know what's happening in there. And ultimately, we should try to use this separated fields method. I mean, this is basically what Eric Hessels has done, what other people have done, but in the crudest possible way. So if we switch over to using the separated fields, then we don't have to worry so much about what the line shapes are doing. We could actually get away with having faster atoms. There will be many, many advantages to doing that, but that's sort of way more advanced than where we're at now. So I think one day we should do this, but before we do this, we should understand what we've already done and make sure that we don't have any other mystery problems. And if somebody else would measure this, that would be nice. It would be great to have some independent measurements done in a different way. I mean, we'll do it again ourselves in a different way, but if another lab would do it, that would be a useful thing too, I think. So anyway, I think I've been talking long enough. So these issues here are all pretty clear. The main problem is I don't think we have a good explanation for the asymmetries, and I don't believe that it's caused by the microwaves or doing funny things in the waveguide, but I may very well be wrong about that. We have improved the uncertainty because we can measure this with many advantages to the previous measurements, but that's basically why we now have this issue here. So we can reduce it more. I think the statistics was the biggest problem. So just getting rid of the magnetic field would allow us to reduce this by quite a bit. I think we could easily get down to the 80 kilohertz that the theory is at if we didn't have any additional problems. So that's something we can do without dramatic changes to the methodology. I think it will work. It'll just take a little bit of time. And I think we need to use these new techniques going forward. The FOSSOF technique, if we could get that to work, that would be fantastic. But I think that's going to take many, many years before we get that far. So anyway, it's not clear what's going on. We've got top people working on it. We need more top people. So I have a postdoc position if anybody wants to figure out how to solve some of these problems. That's one of our top people now who's working on many, many of our problems. Anyway, I think that's enough. So I'll say thank you. And here's just a backup of what we would do for this test of heliums. So thank you very much.
Well, thank you very much. What a nice talk. And a cool experiment.
The Boris Thatcher picture is fantastic.
What is this exactly?
Maybe it doesn't speak too highly of us, actually.
So there were already quite a few questions during the talk, but I'm sure there are many. You can raise your hand, you can put them into the chat if you're shy and I read them, or you can just speak. I think we are so little people that there will be no interference.
Yeah, I have a comment, if I may.
Please do.
I think this is a compliment to Boris. But also I have a question. So there are some plungers that people can use to really change the microwave situation. I don't know if they are conveniently available for this frequency or not, but I personally use them at lower frequencies, and they allow you to completely change sort of the reflections right as you're running the experiment. And so we were able to hunt a lot of systematics this way. You know what I'm saying? It's a plunger that you sometimes called trombone, where you put it in the microwave circuit, and then you can change. It's like effectively having a variable length of your guide, or having some kind of a additional interferometer in it, and then you change completely all the reflections. And if you do have a systematic related to this, that you immediately see just in real time.
Yeah, I mean, for us, real time is like a day because it takes ages to measure anything at all. But I can see the advantage of doing that. But wouldn't it be better if we just had a waveguide that was properly terminated so there weren't any reflections?
Yeah, but then you don't know if you well, okay, then you have to make sure you properly terminate it. But with this thing, you just have a very, okay, I guess it quick doesn't work for you. And then so is going to some more intense positron source, some accelerator or something would be an advantage here?
In principle, yes, but my experience is working at facilities is always a waste of time because you don't have the freedom to do stuff on the fly. The beam time that you're promised is usually, doesn't materialize in the same way. Because it takes us such a long time to get data, if we had a completely clean experiment that we could just bolt on, then I would agree. But with this kind of stuff, I think we're better off having low flux, but 100% access. I've never done an experiment in a facility where, I did some work in Lawrence, Livermore, where they had this giant LINAC a long time ago, and it took like 3 days to persuade them to turn it on. And I worked in the building, so it wasn't like I was coming in from outside. And they had claims of 10 to the 10 positrons, but it turned out to be 10 to the 8. And in the end, it just wasn't worth it. It was far more effort and not enough gain. So if somebody would build a nice facility where you can show up and do stuff, maybe, but at the moment, there's no such place. The place in Munich, they claim to have 10 to the 9 positrons, but you can't get them. You can only get 10 to the 7 because they have to be remoderated and sucked out of a big tube and things like that. So in the end, they don't have any more positrons than I do in my lab. But I would have maybe a week or 2 weeks if I was lucky. So there's no such facility at the moment, but it would be nice if somebody would build one.
How many curies is your source?
50 millicuries.
Okay, good.
And that costs $100,000 and decays in 2.6 years. So, you can't persuade. So this comes from a facility in South Africa called Itemba Labs. And they won't make any higher intensities because they had some problems with the specific activities when they tried to make 100 millicurie, which I couldn't afford anyway. People were only getting 20% more positrons because of the self-absorption. So this is as good as we're going to get for the source, I think. Having more detectors would be a better thing to do. We can just, because we're at the moment, our solid angle coverage is probably not more than 10%. So we're losing a huge amount of data that way. Or detecting, if we ionize the 2s atoms that remain and then detect them on an MCP, we'll get a much better signal. And then it won't be so ambiguous about what we're actually measuring as well.
Cool. More questions? You're looking for QED corrections, or so why are you doing what you're doing?
Well, 2 reasons, I suppose. First one is just testing QED is a worthwhile endeavor, in my opinion. Not everyone agrees with that, but I don't care. The other thing is that if there is going to be some new physics somewhere, then positronium is a good place to look for it because it doesn't have any other complications. So even with the amazing hydrogen, you have to worry about this proton radius issues. Maybe not anymore because it seems like this question could have been answered already. But the point is that there are additional complications in hydrogen that we don't have in positronium. So, maybe there's some funny kind of new axion that only couples to leptons, and you can see it more in positronium than you could in hydrogen. I have no idea. I don't like to make up like bogus models, but I don't think that it's our job to do that. Our job is to do the measurement and then explain it after we know what the numbers are. And so, the fact that there's a possibility of this means that it's worth looking at, given how much emphasis is on this at the moment in the world. Is there a good model that suggests positronium is going to reveal some axions? Not so much. I think people are more interested in muonium for this kind of thing. But we don't know. It's all speculation. So I think just getting good measurements to test the QED is worth it on its own. And if you don't agree with QED, which we currently don't, then you have to ask why is that and find out what's going on. And, I would not put any money at all on there being some new physics explanation for our data, but I still don't know what the answer is. So the goal is to just answer the question. And so if you think that positronium being the simplest system can possibly give you some access to this that you can't get other ways, then I think it's worth looking into that.
Cool. So you're basically trying to improve your error bar or get a result that you can trust that is like either confirming this theory line or is at odds with it.
Well, yeah.
So Dima?
I have actually a question about not about your talk, but about positronium. Just I haven't been following. There used to be a discrepancy in the lifetimes of positronium. Has that been resolved?
Yes. So the lifetime discrepancy came from the measurement technique. Basically, they were making positronium atoms that would collide with things before they decayed. This changed the decay rate a little bit. They thought they had accounted for it, but the way they took it into account made some assumptions about thermalization, which turned out to be wrong. So some people made an experiment where they would do energy cuts so they could isolate the non-thermal part, and this got rid of the problem completely. There's also a problem in the hyperfine measurements, which I think is exactly the same thing. There's some 3 or 4 sigma disagreement with QED in all of the hyperfine measurements. And these guys in Japan have been doing this heroic experiment where they do the same thing. They do energy cuts, throw away some of the data, and end up with this very, very difficult experiment. But this now doesn't agree with the old experiments and does agree with QED. So I think that solution will be solved as well. So there aren't any other anomalies. The 1s, 2s measurement is off by 2 sigmas or something like this. So that's nothing to worry about. So.
David, may I ask? You can rotate a bunch of things in your experiment, or you could at least, right? The laser polarization, the direction of the laser, the electric field orientation that you use for the quenching. Have you done this?
We can't easily do that because, for example, the electric field is made by the ground plane of the waveguide and the bias that has to be applied to the target for impact, and those can't easily be changed. I wouldn't like to try and float the waveguide because I'll probably kill the microwave source. We could make some additional electrodes and have different fields for that sort of thing. But it's difficult to see how those kinds of issues could arise in this way and give us what we see in this data. I mean,
well, I'm still thinking of some asymmetric population of the 2s state somehow, and then you keep driving this, and then different paths interfere, because this is exactly, I think, what you would expect, that one line shifts in one direction, the other one line shifts in the other direction. At least that's what we see in the simple hydrogen measurement, where the 4p 2½ and 4p 3½ lines just shift in opposite directions. And there you can by virtually changing the geometry, by just rotating the laser polarization, we could map the whole functional behavior. And so changing these things may give you a hint on what's happening there.
Okay, I mean, we could look into that. One thing I do know is that ground state atoms are produced with more or less equal populations. There is a slight asymmetry because the positron beam is polarized because it comes from a radioactive source. So there's a little bit more m equals +1 than -1. And there's nothing much. I mean, this is really hard to measure. So the polarization is something like 25% on this level. And that should translate into the 2s population. So there will be some asymmetry on that level in those states. I don't believe that we make any coherent superposition states. I think this is all just non-coherent excitations. So
no. you would be surprised where still coherence exists after decays and so on. So this just solve the Bloch equations. It tells you everything. That's really getting the right line chain model, as you say. This will help. There are some subtle things that you don't expect, and in the end, I mean, you can have back decay, right? So you excite in our experiment, right? We excite to the 4p state, then you have decay back to the 2s state. Still, you are coherent, and so this is not so easy to get a feeling for.
Okay, that sounds interesting. I mean, yeah, we would like to look at these things in more detail. It's a bit difficult when the data rate is so low, but that's not an excuse. We just have to figure out a better way.
No, but you see, if this is a huge effect, right? So in one sense, you can be happy because it's a gigantic effect. You see a shift on the line. Now you just have to figure out how you can, what could be the source of it, and invert the direction, and then you see the gigantic effect in the other direction, and then you may be happy.
Well, yeah, I think so. If it
was
a small...
may be happy, maybe.
Yeah, I mean, we are working on doing the calculations, but it's a bit slow going. I don't know, it's not something we normally do, so we have to learn a lot of things to get it to work. So I tried to get Eric Hessels to do it, and he basically said, no way. In fact, he told me that you guys might be able to do it because you have some code that you're writing for this. But
yeah, Artur Matveyev wrote a code, and he is maybe it's already public, or he's intending to make it public. Maybe you should get in touch with him. He's now in Moscow, but he may be interested in modifying his code for simulating your experiment. That's an interesting question, right? 4.5 sigma, and then these gigantic shifts.
It would be very nice to have a decent calculation. We did do a simple calculation, just including 2 states, to see whether or not we can trust this rule of thumb, and it was basically correct. So it didn't give us any hope that this was going to work. But you know, I think you're probably right that there could be some other thing that is not obvious when you just think about it like this, but when you work it out, you get some big number that you didn't expect. And
yeah, I mean, you have to take into account all Zeeman sublevels, otherwise it will not work.
Right. So yeah, this is when it gets hard to do, because then you can't just run it on your laptop. So yeah, we are working on these things. And the other things that I already said it, but I'll say it again, is that the experiment with the horn antenna, I think, gets rid of some of the issues to do with reflections that were raised. Not all of them, and it introduces some other new issues as well, because the field is very weird looking. But it still seems to give us the same shift. We only tried it so far for this symmetric line. So we still got symmetric lines, and we still saw a large shift in the same direction and of the same magnitude. So to me, that suggests that it's not to do with the waveguides, which is not to say that the waveguides are not, you know, problematic in some other way. But my feeling is that there's something else is going on, and we just don't know what it is yet.
Cool. Are there more questions? While you're thinking of questions, I can advertise next week's seminar, because it's actually the last seminar of this semester. And it's also, we're going out with a bang. It's Stefan Ulmer, and he's talking about studies of exotic physics with antiprotons and protons. So it's going to be very interesting. And David, I'm going to put you, of course, in our email list, and I'm going to send you the invitation, and you're very welcome to join that seminar too.
Thanks. Sounds interesting.
Are there more questions? One last one.
So yeah, what's next is maybe the one. So you have access to the lab, or are you completely locked down because of COVID?
No, I can go in just one at a time, basically. So I go in one day, the student goes in another day. So yeah, we want to do some more. I want to finish this horn experiment just as a test, and then I plan to. Well, I want to try this helium. That's on the next slide here. So basically, I would like to try this, where we just send some Rydberg heliums through, and we will choose, you know, a way to have frequencies that are very close to what we're using in the experiment. I think this will be informative. It won't necessarily answer the question of what's going on in the data, but it will tell us if there is a huge problem with the waveguide, for example. We also need to make it so we can go in both directions. So that will take a little bit of time to do. The next thing is to just get rid of the magnetic field, I think, and see if that's doing something that we didn't anticipate. So that's not very hard to do. You just have to do something called remoderation, where you basically fire the beam into a piece of metal in some mu metal hole, and then extract it with electrostatic lenses. And then, you know, people have done this. It's quite easy to do. It's just kind of fiddly. And, you know, this experiment has all these different steps, and extraction, and then this trap, and then this bunching, and then this electric fields being switched on and off, and they all have to work together. So I always try to avoid adding new steps, and if I can possibly avoid it, but I think getting rid of the field is absolutely necessary for the next level of experiment.
Did you, maybe you have some like unknown background field, is that possible to explain something? Can you reverse the direction of the magnetic field?
No, well, yeah, but it's really difficult because the steering of the beam is a bit dodgy. So if you reverse all the fields, you have to re-steer everything, and it gets kind of hard. We have this magnetic buckle coil which is inside the source, and it's very difficult. I mean, you can't adjust it basically. And I think it's not nice and symmetric. So when you switch it round, it doesn't quite go through the hole properly in the shielding. So This means that you have a problem to switch all the fields everywhere because it doesn't come out in the same place. And when you reverse it, you kind of add to this misalignment. So in principle, it could be done, but in reality, it would be very, very difficult. So I think it's better to just get rid of the field entirely. I mean, the other thing I will say is that, if I can find it, no, never mind. If you look at this point that's been measured in the quadratic expansion, and you just look at it at, say, 20 Gauss, or the lowest fields that we can do, the Zeeman shift there is less than 1 megahertz already. And the data point, that single point on its own, is already shifted by several megahertz. So it's clearly not a problem of magnetic field Zeeman shift that's moving everything in some huge way. There is a background field, but it's like 5 Gauss. It's definitely not an issue. It's also measured and taken into account. So the magnetic field just wastes our time. It means we have to measure 20 points instead of 1. So that's the main reason to get rid of it. But also, it's not a good thing to have in a so-called precision measurement, is to have some stupid Zeeman shift that you don't need. So yes, you definitely need to get rid of that. But I don't think that will solve the problem. It will just make the further experiments easier to do.
So the theory uncertainty looks very small. That is, of course, this voodoo uncalculated higher order terms where people make up numbers or believe in numbers. What is the limit of this theory, and is there any possibility that this can be off by many sigmas?
Well, I would say no, largely because the hyperfine in the ground state agreement is pretty good. So there is a discrepancy, but it's quite small because they're already doing part per million measurements. However, this is on a much bigger number. So they're 80 kilohertz for this n equals 2 level. It's the same calculation. I guess it's possible, but I think I may be wrong about this, but I think if that number was wrong by enough to account for this, then the ground state number would also be wrong by some enormous amount that would be very much at odds with the data. But I have to check that. I don't know. I mean, it's true that it's a guessed uncertainty, but they're reasonably, I think they're reasonably sure about these things. One thing that is interesting in the positronium is the QED corrections are really big. So that, you start getting these giant shifts, and you think, the next order is going to be nothing, but then it can also be like, hundreds of megahertz. So that's why when the original experiment was done in '93, the disagreement with theory was quite big, and now it's perfect because the theory has moved a lot in that time. So I think in hydrogen, it doesn't move so much because they already have the main things down, but we see quite new orders contributing more relative to the hydrogen case. But I don't think it can be this big.
Cool. Well, I think if there are no more last questions, one last question.
I have maybe one technical one. How big is the mesh, and what is the transmission efficiency through the mesh?
The transmission efficiency is quoted, so we don't measure this directly exactly, but it's supposed to be 95%. So if what we can do is move the target out of the way and then put a gamma ray detector looking at the waveguide, and when the positron beam comes through, you would see some annihilation signal if there was a lot of loss in the mesh, and we don't see very much. We can see a little tiny bit, but it's consistent with this 95% transmission.
Mm-hmm. Okay.
All right. So I think we close the seminar here. It's 3:15. So David, thanks a lot for the super nice talk. Good luck with the experiment, finding your asymmetries there, and hopefully we see each other in real at some stage again.
I hope so. Thanks for coming, everyone. Appreciate it.
Thank you.